Okay, this is the third installment of the multivariable calculus saga. Today's video is over the multivariate chain rule for one independent variable. Now, this is applicable in finding the derivative of a, a function dependent upon multiple single variable equations. That single variable being the fundamental equation, or rather the fundamental variable for the multivariable equation. Now, this is pretty easily extended towards multivariate chain rule for multiple independent variables, but we'll go over that on a later date. Today, we're just dealing with one independent fundamental variable. Okay, so as you can see, the process for finding the derivative of a multivariable equation with respect to the fundamental variable is rather quite simple. And what I mean by fundamental variable is the independent variable that the intermediate equations, that is these two, are dependent upon. In this instance, I said it's t, and I said that the multivariable equation is z and can be modeled with x of t and y of t. So the equation of, or d of z, as in the derivative of z with respect to the fundamental variable t, is equal to the derivative of z with respect to x times the derivative of x with respect to t, plus the derivative with z with respect to y times the derivative of y with respect to t. And as you can see, there's a pretty noticeable pattern that is involving the first term with d of x and the second term with d of y. And this is one process that can be employed to find the derivative with the derivative fundamental equation with respect to the fundamental variable. But there are others. For instance, you can simply find, or rather you can simply plug in your equations for x of t and y of t, or whatever your single variable functions may be. You can simply plug those in to your multivariable function, and then they take the derivative. Keep in mind that these are just intermediate equations, x of y and x of t. And so it's quite simple to find the derivative of their parent equation, z. That's really it for the lesson portion of this video. As I said, it's a pretty simple topic. And for that reason, I'm going to dive into the practice problems. This is the first of two. We have a multivariable equation z represented with variables y and x and y. This multivariable equation is equal to x squared plus y squared, where x is equal to cosine of t, y is equal to sine of 2t. We want to find the derivative of z with respect to t. So the first thing I'm going to do is write out the general form for dz dt, and that is equal to the derivative of z with respect to x times the derivative of x with respect to t, plus the derivative of z with respect to y times the derivative of y with respect to t. And from here, we're just going to plug in variables after we find them, of course. And so we might as well do so now. On the second practice problem, I am going to employ the other technique that I told you about. Assuming it's easy, I can't remember whether or not it's easy. But whatever. So the derivative with z, the derivative of z with respect to x, is going to involve partial differentiation. I've created a video over this in the past. In fact, it was about a week or two ago. And it's quite simple. We treat all variables other than the one in consideration as constants. So keep in mind that z is going to be equal to x squared plus y squared. But since we're solving with respect to z, y might as well be a constant. It could be 3 for all we care. And so the derivative of x squared is going to be 2x plus basically a constant. The derivative of a constant is 0. And so that's how we end up with the derivative of z with respect to x is 2x plus 0, which I'm just going to put as 2x. The next term we're looking for is dx dt. Hold on. Okay, so I've already listed the equation for x, it is cosine of t. This portion of the process is quite simple. We just find the derivative of x with respect to t. The derivative of cosine of t is negative sine of t. And so we're going to move on to dz dy, which is the derivative of z with respect to y, which correlates with this part of the formula. Hold on, my bad. Okay, now recall that z is equal to x squared plus y squared. Now x squared, since we're not deriving with respect to x, is going to be a constant. The derivative of the constant is 0, and so that term of the derivative is 0, plus the derivative of y squared with respect to y, which will, of course, be equal to 2y. The final term, dy dt, we simply have to find the derivative of y with respect to t. This over here is y, the derivative of which is equal to 2 cosine 2t. Now, funnily enough, in order to find the derivative of y, we actually had to employ the Cartesian single variable chain rule, which I've made a video on in the past in case you're interested. But all we have to do now is just plug in our variables to our general equation up above. I'll write it down here. dz dt is equal to dz dx, which is 2x, times dx dt, which is negative sine t, plus dz dy, which is 2y, times, times 2 cosine 2t. And so we're going to move the 2 to the forefront of this term. That's why I'm changing it to 4, since 2 times 2 is 4. Cosine 2t. Okay. Unfortunately, we're not yet done. This is what's annoying about the multivariate chain rule. You need to plug in, or at least when using this method, you need to plug in the fundamental equation, or the single variable equations that your parent multivariate equation is dependent upon. So x and y are going to have to be replaced by cosine of t and sine of t. Now, I'm not going to simplify this equation because I don't like to, honestly. But nonetheless, you'll get the gist of it, hopefully. So once more, dz dt is equal to negative 2x sine t. However, x needs to be replaced with cosine of t. And so this term is going to be equal to negative 2 cosine of t sine t. Plus 4 times y cosine of 2t, but y has to be equal to sine of 2t. And so we're going to replace y with sine of 2t, which results in 4 sine of 2t times cosine of 2t. And that is the derivative of z with respect to t of our multivariable equation. And so now we're going to move on to the second practice problem. Okay, this is the second practice problem. We're given a multivariable equation, f of x and y. It is equal to x squared plus 2xy, where the variable x is represented by 2r, and y is equal to e to the power of r. Now, this is exactly the same as the last equation. The identity of the fundamental variable is not relevant. It doesn't matter if it's r or t or theta. We're going to treat it the same. So we might as well do so. dz dr. Now, as I said, I'm not going to use the process employed last practice problem. I'm going to do a new one. I'm simply going to substitute in our single variable equations, x and y. That color is way too dim. Into our parent multivariable equation. And from there, I'm going to take the derivative. So instead of, listing out the general formula, I'm just going to say z is equal to 2r squared plus 2 times 2r e to the power of r. Now, why did I do this? As I said, I simply substituted in the functions for x and y. 2r goes over here, as it does over here, and y goes over here. And so that's how we have this as our multivariable equation. I'm going to simplify this further, and I'm going to do another color to do so because I'm bored. So z is equal to 4r squared plus 4r e to the power of r. Now, once more, I'm going to switch color. Okay. To find what we're looking for, dz dr, we're simply going to take our variable, our function d, now represented as a single variable equation, and take the derivative of that with respect to r. And so we end up with dz dr, as in the derivative of z with respect to r. And we're simply going to take the derivative of each term with respect to r. Using the power rule, the derivative of 4r squared is 8r. And now using the product rule, the derivative of 4r e to the power of r is 4 e to the power of r plus 4r e to the power of r. And that's it. I don't know if you can simplify. You can most likely simplify this further. I don't feel like doing so. So I'm just going to say that this is the final equation. Notice how at times this can be much simpler than the former process employed. But, contrarily, it can also be more difficult. But that's it for today's video. This was a short one, I hope. Please leave suggestions for any future videos. Thank you.